project, which, like I said, is just basically an extension of the one that was due today. And it's unloading sand, okay? The unloading sand project. So this is unloading sand onto a scale. The red graph is the rate of change of weight as a function of time in seconds, and that rate of change is in 100 pounds per second. Okay, so we're unloading like from a truck, like they're tipping the truck bed up, and the sand is unloading onto a scale, and this is the rate of change of weight as a function of time. Why does it make sense that the rate of change would look like this red graph?
Because when you're tipping the truck,
yeah,
only a little bit can get out because the mass of it is still in the middle.
Okay.
Then you tip it, and then it has a higher angle, so a bunch of sand falls out all at once.
Right.
And then you tip it some more, and just a little bit more trickles down.
What do you think? Does that make sense? Yeah. So you can imagine, right, when the truck is tipping up, a little bit will come out at first, then a little more, and then in the middle is when most of it will rush out, and then there'll be a little bit left over at the end. So this kind of follows what you would imagine as the rate for sand coming out. All right. So, like, let's see. All right. So that's not, I'm not on the right view here. So then you're going to have some views here. All right. So view 1. Shows the rate function, okay? Shows the rate function, and then it being generated for increasing value of x. View 2 so this is what you did, right? This is what you did?
Yeah.
Or worked on. View 2 then shows for a given delta x, here I can set delta x, I've got it here at 0.3. For a given delta x, it's going to show the approximate rate function using left sides of each interval to be the constant rate in that interval. And then, again, using the n slider, it generates that function. View 3, and then you also see that and maybe this is what this is showing now over here is showing the exact what do you imagine that is over there? Yeah, so does this make sense? This is the accumulation of sand, right? It's going to accumulate slowly at first, then in the middle when the rate is high, it's accumulating quickly, and then at the end we just get a little bit more added onto the top, and then we have kind of the final amount there. Right? And so then view 3 shows the approximate accumulation function being generated along with the approximate rate function. And so now our accumulation is there over on the right. So this will be the new part. But you have all the tools. Really, this is going to be the hard part of this is what you've done already. Okay? You have all the tools. We just have to go back and find them and put them together. So in view 3 would be the approximate accumulation function. I think maybe. Okay, so I think view 4 was then, that's supposed to be the exact accumulation. Somehow in my file it ended up on view 2 as well, or view 2 through view 4. But view 4 then would be the exact accumulation function appearing. And kind of showing this is kind of like this mysterious goal that we have, right? We can form the approximate rate function and have this approximate accumulation function with the goal in mind that exists somewhere in the ether exists this actual exact accumulation function, which this approximate accumulation function is trying to replicate, right?
So the exact one is the gray one, right?
Yeah, the exact one is the gray one, and then the purple one is, hand in hand with the blue approximate step rate function.
So for view 2, what do you want to be seeing?
View 2 would just be over here on the left, right? So View 2 is just the approximate rate. View 3, add approximate accumulation. View 4, add exact accumulation. The gray one. So my file, the gray one got put in like views 2 through 4. Okay, but yeah. All right, and then if you change delta x, everything changes accordingly. So I'm going to change delta x to now about 0.2, and now I've got my constant rate function as at intervals of 0.2, and likewise the approximate accumulation function is piecewise with intervals of 0.2. And so the whole point of this is with smaller intervals, you all know with smaller intervals you get a better rate function, a rate function that better replicates the actual rate function, and an approximate accumulation function that is approaching this mysterious exact accumulation function. So somewhere along here in delta x, I think it was maybe 0.04 about. So when you get to 0.04, again here's like 0.05. When you get past 0.04, then the exact rate disappears, and all you see is the approximate rate. But this is the idea that when you get intervals small enough, the approximate rate is virtually the exact rate. And so I've called on this program, on this file, I think I set the limit at around 0.4. So this is 0.0463, maybe 0.05 or something. It looks like, yeah, maybe 0.05 is where I made the cutoff. But yeah, so at 0.04, for delta x smaller than that, then you can have the exact rate go away. And then here I'm showing it all the way to delta x of 0.005, which is still showing constant rates, this approximate rate function, but now it's so close to the actual rate function that it looks like a curve, right? It looks like the curve of the original rate function. And then what happens now, your approximate accumulation function is basically reproducing has arrived at the actual accumulation function on the right. Okay, that's working. We're making GC work hard with those really tiny intervals and the accumulation over there on the right. So finding the y values, adding up all those little bits of change from all the intervals, so it's making GC work really hard, so that's why it's slowing down. Okay, so questions on the assignment. So basically the new part is this new, the new window over here. It's the accumulation window showing approximate accumulation, and then as delta x gets smaller, approaching exact accumulation. Yes, ma'am? Oh yeah, no, that's given. So that's up here. That's this and unloading. And then so I'm using capital R as exact rate. If you want to use subscript like R sub W, like I'm showing there, that's fine. I just use capital R for exact rate. So this should work. If you change the rate function, everything should change accordingly. Now the scale might not be right. So this scale and this text up here is all based on this particular rate function, the stand unloading. But your file should work if you change the rate function to something else. It should generate an approximate rate function that works and the according approximate accumulation function. Other question?
What is the equation right there? The one that's hidden, the y equals r of x?
I'm about to talk about that. Don't worry about that right now.
Do we have to write that in our file? Like of the unloading stand onto a scale? Sorry.
Oh,
do we have to put that on ours?
it's less important. Less important. Yeah, but you know, when you think about actually making didactic objects for your students, you want the visual to be as clear and helpful as possible. So you do want things like that. But at this point, I'm more concerned with that you have the mathematics right. Yeah. Other questions? Okay, so I want to talk about this a little bit more here in terms of the one that you were turning in today. It kind of occurred to me as I was helping some students that this idea of the animation of the function, showing the function being generated, is important, and we've talked about why it's important for our students, and that we want them to see what the covariation of two quantities, right? We want to display how y covaries with x. There was some point in time when x increased and the y values kind of were produced or generated or emerged, right? And so we want them to have that feeling for when they see a graph, this dynamic version of a graph. But what I realized was that this may have kind of been a little bit of a distraction for you creating the file, because you get focused on how do I make the lines appear and then the old lines stay. All right, so this is the wrong way to think about it, because what you really want to think about is, how do I create the approximate rate function, the whole thing? So this is what I'm showing here. I'm just going to turn it on. R of x. This is what you want to do. The animation part is a simple afterthought. Okay? We want to focus on how do we get this function? How do we create this function? And then if I need to, all I have to do is change delta x. And it works. Okay? So that's, if you were still working on that, or forget about the animation when you're creating this, and just figure out, how do I create this function r of x? These purple steps that I'm showing. Then you can display it such that it only displays up to n. That's easy. That's easy. That's just putting a condition on this when you display it. So this, it just occurred to me as I was helping students. So I would have definitely talked about this before the project to help you, but it just really never occurred to me until I started talking to some students about it. So does that make sense? Mm-hmm. This is really, in doing this project, your focus was to figure out, how do I create this function r of x? And then it's the whole thing. It's not one step at a time, and then how do we get the old ones to stay? It's, you create the whole function. And so if you write y equals r of x, it shows the whole function. And then you just use n to just reveal what everything up to n. You just show x values up to n, and then when n changes, it reveals it. Whatever, we're already there. Okay, so sorry that I didn't prep you that way before. If I would have thought of it, I definitely would have. And so you get more time now, and so does that help?
Yeah, it's simple.
What's that?
It's simple.
Okay, yeah, so that's the idea, that the mathematics of creating this function is not about the dynamic aspect of it. It's about getting the whole thing, and then adding on the just as an afterthought, how do we animate it up to n? Just show everything up to n, and then just let n increase. So that's the easy part. Yeah, questions, comments?
I have a question about your graph. So you're saying that a truck can be unloaded in 2.4 seconds.
Yeah.
Okay. Just wanted to ask.
Yeah, that's only what? It's not even 500 pounds of sand. That's not very much sand. It doesn't take much sand to weigh 500 pounds. It would just be a little pile in this corner,
100 pounds per second. So 2.4 would be 240 pounds. 240 pounds total, right?
What's that?
Because it's 100 pounds per second, so like 2.4 seconds later, you're dropping 240 pounds, right?
Total?
Yeah.
No, it's about accumulation, right?
I get
This accumulation function tells us there's how much in the end. 0? Did I mishear something? So what does it say? So by the end of the 2.5 seconds, how much sand was accumulated on the scale?
450, I guess.
Yeah, a little less than 500.
Okay.
That's not much sand. That's not very much sand. They could easily fall out of a truck in 2 seconds.
So Tuesday, this file is due?
Yeah. So this one's due Tuesday. And, so a couple of things that you might need. And the first is summation, okay? If you want summation on GC, Control-Shift-S. Lets you set up a summation, okay? And you can use that as part of an equation. You can use that as part of a function, all right? You can make a function that is a summation function, okay? The other one is integral, Control-Shift-I. And then you can change the rate function. You can alter your variable on x. You can change the dx to d something else. Okay.
But these aren't necessary for this project, right?
What's that?
These aren't necessary for this unless we want to do it, right? Or are those both necessary?
I'm not wasting your time.
Okay, true.
I'm not wasting your time.
I'm saying,
okay?
They're necessary.
Do we need one or both, or what? Both?
These are things you might need for the project.
Might.
Any other? And if you come across you need to do something and you don't know what the thing is, just email me and say, hey, I'm trying to do, like we had floor and all these other functions. So if there's something else that maybe I've forgotten, but I think I've gotten everything now. But that's Control-Shift-S for summation and Control-Shift-I for integral. Okay. Any other questions? Yeah. Good.
So if we want to look at a project database, do you have any sites you would recommend?
Oh, just read we didn't really read through the thing. Just read through. There's some specifics on there.
Oh, really?
Yeah, just later. Do that later. Okay. Yeah. And if you read through, it'll be plenty enough for you to get some ideas going. Okay. Okay. So let's actually use this file to talk about where we've been and kind of summarize things here. So this has been our little journey here on, how fast something is changing at every moment, and what you're looking at up here. What is that? What is, how fast something is changing at every moment? What is that? In this particular example. Rate of change? What'd you say? The left graph. Which one? There's actually two functions over there, right? The red one, right? You know how fast something is changing every moment. You know exact rate of change, right? You want to know how much you have at every moment. Where's that on the screen?
Exact accumulation.
She said exact accumulation. You agree with that? Autumn, you agree with that? And which one is that? What's that? Yeah, the gray one. Oh, sorry. Just be glad you had an easy question, right? Give me this crazy look on your face, like. All right, yeah. So we want the gray one as the exact accumulation. All right, and so how do we do that? Right? If the rate is always continually changing, no small task, right? This is difficult. So what do? How do we? If we have a continually changing rate function, then what do we do to get from the red graph to the gray graph? That's not what we did. We did 3 weeks of work. We didn't just do integral. We did 3 weeks of work to get from the red graph to the gray graph. So, Jessica, how did we do that? Mm-hmm. Okay, that was the formula we came up with. But what was the first thing? We've got this changing rate graph, and it's kind of impossible to get any amounts make any headway towards accumulation. So where did we go? Yeah, good.
So how we got accumulation in this thing?
Mm-hmm.
We added the completed intervals.
We added intervals together. We add intervals together?
We had to get our constant
Okay. Right, so we needed constant rate of change, because without constant rate of change, we can't make any headway towards accumulation. But with constant rate of change, what do we know? So that's our blue graph, right? So with constant rate of change, how does that allow us to make headway towards accumulation? Andrea, do you remember?
If you take the constant rate of change and multiply it by the change in x from the beginning to the end of the interval, you will have an approximate accumulation.
Good. Right. So if we took any constant rate times the change in x, it gives us?
Your change in y.
Yeah, a little bit of accumulation, right? And that came from the idea of dy equals mdx. And so then what was the whole basis of the approximate accumulation function? Just, we came up with this thing, so a of x is essentially what? So now I want to write the whole thing out, right? So we came up with the full version with all the details, but what's the overall idea behind that a of x function? So you know?
I think I do.
Okay, so.
A of x is the approximate accumulation
Okay.
Based on the constant rates of change. I know there's more to it than that.
Okay, yeah, that's true. And so but what was the kind of the formation of that function, or the general mathematical idea behind that function? Yeah. Okay.
So you would add up all of
Add up, how do we say that?
you do the summation of all the completed intervals.
Okay.
And then you would add that to the current interval you were in.
Okay, and so we can even step back a bit further, because completed intervals and the current interval are just all intervals, right? So in this essence, what are we adding up? Brandon, we're adding up what to form this accumulation function, a of x? Yeah, and so what is that? Yeah, how would I write that? Yeah, right, exactly. So it's like r of x we just summed up little bits of accumulation in intervals, right? Rate times change in x, rate times change in x. Okay, and then in order to then make progress towards the exact, so that's an approximate. What about making progress toward exact accumulation? What was that about? So how did we do that? Kelly? How would I I've got this approximate accumulation function, which built on summing up these little changes, these little bits of accumulation. Rate times change in x plus rate times change in x plus rate times change in x. So now how am I going to move toward the exact accumulation?
Wouldn't you times it by x, or would you work with large x?
So I've already got it times delta x, and I want to get a better version of this, right? I want to get a better version of a that's closer to the exact accumulation. Jesus, what do you think? Okay, so then what does that mean about the intervals? Right, so from here we want to do smaller intervals, right? And so the smaller I make my interval, the better I do, right? So that's what this awesome file that you're about to create does. Until we're so small that we virtually have the a sub w function. So the ax function, its basic rule is this. So we know it's a lot longer and more complicated than that, but that's it in a nutshell, summing up bits of change. Okay, but then when those intervals get small enough, we can write this a different way. The lesson. Yeah, Britt.
How do you actually say argument?
What's that? times x? Not times x, because x is all the way from 0, right? But yeah, you're right. So when things get really, really small, it's like we no longer have all these discrete constant rates, but it's like we take we're really virtually getting every single rate multiplied by each rate multiplied by big interval or small interval? Tiny, right? Tiny interval. And then that's it. Is that right? Yeah, how do we add them together when they're super small like that? Yeah, this is the idea of the integral, right? Okay, and so that this is it represents this bad boy that we came up with, right? This ugly, very detailed function that had the sums and all these different functions in it, left of x and a plus j's and all these things, right? So when it comes down to it, when delta x is very, very small, then we rewrite it this way. So what's the same about these two? What's one thing that's the same? How do you see that the a function and the aw function are showing the same thing? So what's one thing that's the same? Rachel. So what's this? What's the parallel in the notation? How do you see that this is virtually the same as this? See anything that looks similar to you? Okay. So our interval, right? Delta x becomes very small, dx. Okay, what else? What else is the same? Leo. Right. So this is our like discrete constant rates, but then when delta x goes really small, it's like we take all of them, right? We take the whole continuous rate function. What else is the same? Yeah. Anything else that's the same? Or parallel, right? Parallel. We already talked about, yeah, so we can't, they're not the same, but they're parallel, right? They're both a little change in x, this being a very, very small change in x. So yeah, so those are parallel to each other.
In the summation one, you're adding stuff up together.
Yeah.
In the integral, you're adding stuff up together.
Right, exactly. So they're both, this is like German s, oh, this is German s, that's what the integral symbol is. And this is Greek s, sigma. So we're adding up, okay? So this is just a lot more concise, compact way to write that long function that we worked on for the approximate accumulation, right? Okay, but what it comes down to, that long approximate function comes down to this, right? Which for small intervals, then we write this way. Okay, and we start at our initial value, a, and then we go to x. All right, but this actually is not correct. We have to use a different variant letter here. Why do we have to use a different letter? So I can't use RWX and DX.
Wait, what about the outside, the AW of x? Is that okay?
Yeah. Yeah, so we want it to be a function of x, the current value of x. So we want to integrate from a to x, RWT dt. And why do we need this new letter, anybody? Why do we need that new letter? Okay. Uh-huh. Okay. Yeah, let's write out this way that seems the same, but it's not. I knew I wasn't going to make it. Okay, so here's the alternate version. I'll call it A star, where it's A to x, R sub w x dx. So the way that you can think about this is, how would AW, say, of 1 versus A star W of 1, do those give the same thing? And if not, what does each give? How are they different? So I want you to do a little, just at your table. So what would AW of 1 be? And what would A star W of 1 be? The one that has the x's within the integral. And what would they be the same or not? And if not, how are they different? Okay, yeah, that's the key. If you do A star W of 1, it's be what? The integral from A to 1 of what? RW of 1 dx. So what's it going to do? It's going to start from A, in our case A is 0. It's going to start from 0 and it's going to accumulate at what rate? Yeah, it's gonna accumulate that whole way, all the way from 0 to 1 at this rate, the rate that's represented by that point. So it's really going to accumulate at a constant rate like this. Is that what we want? No, we want it to accumulate as at all the varying rate, right? At the varying rate. We want it to accumulate at all these varying rates starting from 0 to 1. So t is a value of x, and it represents what? Every value of x from a to x. So that as we vary from a to x, we get the actual rate function, or all those little constant rates, instead of just one single rate equal to the rate at the end of x. Okay? So yeah, so that's why that doesn't work. Okay. And so what we said before, what is the underlying principle of this whole thing? Whether it's the approximate rate function or the, let's erase all this stuff now. All right, so whether it's the approximate accumulation function down here or the exact accumulation function, what's the underlying principle of this? What's the underlying principle? You all know you just... Yeah.
Adding rates of change times a small change in x.
Okay.
Adding them up.
Okay. Yeah, so summing up little bits of change, that's true, but even so, more foundational underneath that is what? Okay, so this is the approximate rate of change down here. So for both the approximate rate of change and the exact rate of change, what is our key underlying feature idea? What's that? Little bits of accumulation found by? Bottom. Constant rate of change, Rex. Constant rate of change. How do you see constant rate of change in here? MDX, right there, summing up little bits of change by MDX. How do you see it in integral? MDX, right? It's just the continuous rate function, each rate times a little change in x. So again, this is not GIF. All right, so this is why this program makes such a big deal, and the Pathways curriculum and our revised calculus curriculum makes such a big deal about constant rate of change and understanding constant rate of change. We spent like 3 weeks on it, right? But then we kept talking about it because we were talking about this. Because constant rate of change makes up the heartbeat of an integral. Calculus, right? Calculus, an integral. That's constant rate of change right there. Rate times a little change in x gives you a little change of accumulation. All right, did they teach you this in high school? What did they teach you integrals about in high school? So, what did you learn about an integral in high school? It's okay, you can say it. Area, right? Okay, so where along this process could we might have gotten sidetracked and gone off into area? So what does area have to do with this? So, and you know, I want to talk about area, right? So that this is this is the predominant mode of thought about integral, that its area has to do with areas and area under the curve. So how does our whole context of accumulation and rate of change then relate to area? Not sure? Noel, any idea? Where would area come into this?
Well, I learned that we were like taking like infinitely small boxes.
Okay.
So.
So now I'm making big intervals now. So that'd be for small intervals, right?
Yeah.
So I'm showing big intervals now. So
Yeah.
where would these boxes be?
So the box would be the side of the blue line, the length of the blue line would be one side,
Uh-huh.
and the height would be the RW or the R of X. So it's still an M times a small change in X.
Okay.
But we just thought about it in areas of boxes instead of adding it up.
Okay. Instead of rate of change and accumulation. So do you see what she's talking about? She's looking at the left graph or the right graph? In the left graph, whenever we did this rate times delta x, that also happens to be the area of what? Rectangle, right? Delta x being the base, and the height being the rate on the left side, right? So that's the y value of this function. And so then that's r of x for this rate, right? And so when we summed up these r times delta x, it could be construed as or applied to the fact that that's also the formula for the area of a rectangle. Width of the base times the height each time. Width of the base delta x, height being the rate. So, which is it? Which was it originally?
The boxes.
The boxes came first. Is that right?
Well, in our education.
Yeah, right. Okay, so when I'm talking in the grand scheme of things in mathematics, so in I guess mathematics education in the U.S. So mathematics education in the U.S. somewhere along the line, 50, 60 years ago, and maybe it's an evolutionary process, but integral got hijacked by these areas of these rectangles. Okay, these areas of these rectangles, it's just an artifact of the fact of the way that we graph. The fact that we graph x on horizontally and y vertically, that's why this works out this way. That this bit of accumulation also turns out to be the area of a rectangle. If you change the way that you graph, then that won't hold anymore. Okay, so it's about the way that we graph with the axes perpendicular to each other like that. Okay, graph this in polar coordinates and it won't work. Right, polar coordinates is angle swept around the pole and distance from the pole. So your rectangle thing is out the window. Okay, so it's only kind of incidental to the way that we graph that this thing ended up being another way to see it is its calculations is areas of rectangles added together. But it's not, so that the area thing is not really a profound meaning, right? It's just applying the formula of a rectangle.
What does it say about the accumulation?
What's that?
Does it have any impact on what it says the accumulation is? Like the volume thing? How are volume and accumulation connected?
Right. So the connection is the final answer, the final value. If you were to add up, so like say a 2.5, if you were to add up the areas of these rectangles, the value that you would get would be the same as the amount of accumulation, the approximate accumulation from this purple graph. So the ending numbers are the same. That's the only thing that's, because of all the numbers, the calculations are the same. It's just, are you viewing it through the lens of accumulation and rate of change, or are you viewing it through the lens of geometry, right? Base times height plus base times height. But the calculation, all the numbers are the same, and so the final answer is the same. So, the question is, what does area have to do with weight of sand? What does the area have to do with weight of sand? Nothing, right? So why do we talk about, oh, the weight of sand is the area under the curve? No, it's not. It's the weight of sand. And how did the weight of sand come about? Oh, it came about by adding these areas of these rectangles together. No, it didn't. It came by adding together little bits of weight of sand. You see? But this is the language we've taken. All calculus has gone to this language. Oh, the weight of sand is just the area under the curve. It's just it's the sum of all these areas of these rectangles. Okay? No, that's just kind of just incidental. It's just kind of an accident that happens because of the way that we graph perpendicular x and y. So we can take our bits of accumulation and say, oh, that ends up being the same as length times width. So that means that anytime you have a rate function, say, anytime you have an integral, you've done tons of integral problems in calculus. What is that g of x? It's a rate of change function. It's a rate of change function no matter what context you're in. G of x is the rate of change of some quantity, and then the integral is giving you. What's the integral giving you? It's giving you the accumulation of that quantity given that you know its rate, g of x. Okay. Learning new things, right? Okay, any questions on the project or the meaning of integral function? Last chance. I'm gonna erase. Okay, so let's change gears a little bit for a little while so after the assessment. So no, I've changed my mind. Let's do the idea for your project. Do the Tuesday after that, because I think I want you to focus on this project for Tuesday. Focus on the assessment for Thursday, and then we'll do the idea. We'll push the idea back to a week from Tuesday. Okay? Yeah, I think it's too much for 1 week. Okay, so let's see. So, and then after the assessment, we're going to kind of continue this conversation. We're actually going to look at the reverse idea. You know how much of a quantity you have at every moment. You want to know how fast it's changing at every moment. So, I'm sure you can kind of guess what that's about. But like this, it's going to be, you're going to learn new things, right? It's going to be a totally new perspective than what you've seen before. Okay? So we'll pick that up after starting that Tuesday when your idea is due. But in the meantime, I want to start another little topic here. And so to introduce that, I want to show you this this question here. So we're going to take a slight break from the calculus stuff. And talk about something new. So a caterpillar walks on a wall from point A to point B along the path shown. Is the caterpillar's height above the ground a function of time elapsed since the caterpillar started moving from point A? Okay, so I want you to grapple with that with the people at your table. And so as a hint to help you, start by defining exactly what your independent quantity in this relationship is and your dependent quantity in this relationship to determine if you have a function or not, right? So do you have a function or not, and why? So identify thoroughly what the independent and dependent variables are, and then talk about this question.
That's just the path.
Okay.
Right. What they all said.
What they all said? Okay. Oh, you guys are so smart. All right. So, and I'm not surprised. What's the independent variable? Time since starting to move. And the dependent variable? Height above the ground of the caterpillar. And so, it is a function or not? You guys think it's a function? You guys are being quiet at the table. Brandon, what were you guys talking about? What do you think? It wasn't. Why not?
I'm not. I said it. I didn't say it. And if it's wrong, I'm not going to get blamed for it.
I'm done. No wonder.
Jesus brought up something about going backwards in time. Or saying it like that. See, I'm letting them speak for themselves.
As time increases, the caterpillar could walk like could get closer to the ground,
Okay.
further away from the ground. Like time doesn't tell you. Like I don't think time is like always at this point. I don't really know how to say it. I don't
So you're making an argument for why it's not a function.
Yeah.
Okay? Others? Jessica?
He said it was a function.
Okay.
Just that graph that is there is not the actual graph of the function.
Okay?
But that graph would be the path that this caterpillar took all over the place.
Right.
But if you were to graph the function between the independent and the dependent variable, that would not be the graph, and that it would be a function.
And why would it be a function? So you're saying if you actually graph this, these two variables varying together, you would get a function. Why? Why would you get a function?
Because for every time since it started moving, it has a different height.
Okay. Sophia, what are you?
Yeah, basically, like, the caterpillar can only be in one place at like one time, basically. Even though the path is going like backwards or forwards, time is still going on.
Okay. Andrea, you agree?
Yes, I do.
Because what is the definition of a function? Given
Any x.
for every, or sorry, not given, for every, right? For every value of independent, there's only one value of the dependent. So so for these variables, is that true? Given any time since it started to move, is there only one height assigned to that time?
Yes.
Yes, there is. Okay. Yes. So yes. So now this picture is showing a function or not? What are the two variables for this one? So the independent variable would be, how would you describe the independent variable here?
Ground.
Ground is not a variable. What variable is being shown on the horizontal axis? If that's the path of the caterpillar, then what variable is it showing? What's that? Not the length of the wall. But you got the right idea. What's that? The distance he travels? No. So you're asking yourself, for any point on this curve, what is the x coordinate representing?
Wherever he is in location on the ground that's compared to the start of the wall or where he started.
Right. This is horizontal distance from the wall, right? So this would be like horizontal distance from the wall. Would be that variable. So if height above the ground, you're saying, is not a function of horizontal distance from the wall. Agreed? Okay. So this curve is not a function. Okay? But I offer to you that it could be a function. That curve could represent a function. And so now I want you to think about what could that function be? This particular curve. How could this curve be a function?
In terms of distance and height?
I didn't say that.
Right.
Well, I think we already decided if it's distance and height, it's not a function. So how could that curve still be a function? So that's what I want to talk about. How could we see that curve still being a function somehow? Go. All right, what if the independent variable, we go back to time? Time since the caterpillar started moving. It's unique for every time. What is unique for every time that's gone by? Both, right? And how could we sum that up together? What could we say? Given for every time the caterpillar has exactly one location. Location. But in order to pinpoint location, what do we need to pinpoint location?
Three axes.
What's that?
3 axes.
Not 3.
You need the height and
You need 2. Yeah, you have two variables, right? You have 2 quantities that will give you the location. So it's like I don't know, horizontal and vertical, say. Horizontal distance, and the H is not for height, it's for horizontal. So horizontal distance and vertical distance. So these 2 taken together can be thought of as one function, the function of the caterpillar's location as a function of time since he started moving. Okay, and you've done this before. What kind of function is that called? Anyone know? Not piecewise. Parametric function.
Parametric? I don't remember that. Did you bring that up in class?
Calc 2.
Yeah. Okay.
You should have had that in Calc 2. Parametric functions. This is the idea of parametric functions. That you have this independent variable, and then the dependent variable may be, quote unquote variable, may be a combination of 2 or more other variables, right? So location is uniquely determined by time, but that requires 2 functions taken together, okay? And so that idea is a parametric function. So parametric functions allow for all these crazy curves like that, all kinds of curves in the plane that you would have written off as non-functions before if you were doing y as a function of x, right? So this is certainly not y as a function of x, but location ordered pair x comma y is a function of a parameter, in this case time. Okay, so this, like I said, this allows for how about that one? So this is so crazy function, right? But look at the formula. It's not that crazy, right? X is t plus sine of 2t, and y is t plus sine of 3t. Those aren't that complicated, but then your curve is wild, right? Let's look at some others here. So that's the one up there. Reminds me of Star Trek, is what. This one's going to be less exciting. What is it?
Probably
Now for this one, notice that you could rewrite this as an equation of x and y. How can you rewrite it as an equation of x and y?
y equals 1 plus 3.
So y is 2 minus t squared. And how could we rewrite that in terms of x? 2 minus, well, that's t, not x. So what is t? X minus 1 divided by 3 squared. Right? So because t is x minus 1 divided by 3. So what is this thing? So y equals 2 minus x minus 1 squared over 3. It's parabola, right? That's parabola. That's y is some function of x squared, right? So this is a parabola. So parametric functions, if you want, can be used to reproduce common functions that we know, but then they allow us to write all these ones that, or define crazier stuff too, like a particle, something moving according to time, right? Something moving in the plane according to time.